Picture scheduling final exams for a major university. You have thousands of students, hundreds of overlapping courses, a finite number of rooms, and a strictly enforced window of time slots. One tiny overlap and the whole system crashes. To solve this logistical nightmare, computer scientists strip away the chaos of the real world and convert it into a pure mathematical puzzle. We call this a graph coloring problem. Let's start with the mapping. We represent every individual examination as a single point, which we call a vertex. If two exams conflict, we draw a line connecting them, an edge. A conflict usually means one of three things. A student is enrolled in both exams, they require the exact same room, or faculty constraints mean they cannot occur simultaneously. Finally, we introduce colors to represent our available time slots. Our ultimate objective is to color every single vertex on the graph using the absolute minimum number of colors. The rule is that no two connected nodes can share the same color. Achieve that, and you've guaranteed a conflict-free exam schedule. Looking at Section C of the assignment outline, we see the overarching hyper-heuristic framework. Think of this as the manager program. The manager initializes the graph, iteratively selects and applies low-level heuristics, evaluates the resulting timetable, and accepts improvements until a termination criterion is met. If the framework is the manager, the low-level heuristics are the workers actually coloring the graph. Let's look at the first worker, the largest degree heuristic. This standard 5-node graph shows the static largest degree heuristic. Before coloring, it counts each node's connecting edges, sorting them from largest to smallest. Here, B and C tie with 3. It then straightforwardly colors the highest degree nodes first, using the lowest non-conflicting color. Because it calculates edge connections only once, largest degree is computationally fast. However, its static nature means it strictly follows its initial list. It cannot adapt to the scheduling bottlenecks that form as the graph fills up. To solve that rigidity, we use an adaptable alternative, the saturation degree heuristic. Saturation degree prioritizes nodes with the most differently colored neighbors. Starting uncolored, it breaks the tie by initially coloring the most connected node. The tracking table then immediately updates adjacent nodes to 1, demonstrating it dynamically recalculates its internal rankings after every single move. This continuous move-by-move recalculation is where the algorithm diverges from static methods. While it requires more computation at each step, this dynamic updating allows the solver to adapt to tight scheduling corners as they emerge. When we compare the final outputs side by side, we see how dynamic heuristics often discover more efficient scheduling patterns compared to a rigid, static approach. A graph-based framework allows adding new constraints as simple edges and provides a structured way to navigate millions of combinations. Furthermore, this approach handles varying departmental sizes and maintains modularity by separating the problem model from the search algorithm. To summarize, we began by mapping exams and conflicts into a graph, moved to the loop the manager uses to search for solutions, and looked at the low-level heuristics that color the nodes. Abstracting the real world into a mathematical graph, structuring the search loop, and managing dynamic feature updates provides the necessary structure to resolve complex examination timetabling conflicts.